In this video, we're going to do a proof example. So proofs can be tricky, they can be more conceptual and more challenging, but I want to do an example where we sort of break down some of the steps behind proofs and we talk a little bit about proof strategy. So this example is going to involve part of the invertible matrix theorem. So I'm calling this invertible matrix theorem continued because I'm stating a couple parts of the invertible matrix theorem that I didn't do in one of our previous videos, but the textbook has both of these. So part of what the invertible matrix theorem says is a matrix A that is n by n is invertible if and only if there is an n by n matrix C such that C times A equals the identity. So when there's a matrix C that I can multiply A by on the left to get the identity, the matrix A is going to be invertible. Similarly, my matrix A is invertible if and only if there's an n by n matrix D such that A times D, so I'm multiplying D on the right hand side of A, equals the identity. So this is going to be useful in this example. Okay, so let's read the example and get into it. So suppose A and B are n by n. If A times B is invertible, I want to show that B is invertible. Okay, so here's my example. So one quick comment is when a problem says to show something, that's another way to say prove this. I want to prove that B is invertible. So one technique that I have to deal with proof type problems is to organize my work by first doing some scratch work. And the scratch work, I like to organize my thoughts into two columns. One column where I write down what I know, and the other column in which I write down what it is that I want to show. Or I'll abbreviate that as WTS. So a know column and a want to show column. Okay, so what is it that I know? Well, one thing that I know is that A and B are n by n. I'm given that A and B are n by n. And then anytime I have like an if-then statement, like in this case I have if AB is invertible, then I want to show that B is invertible. So anytime I have an if-then statement, what is after the word if? So in this case that's A times B is invertible. That is also something that I'm given. So I want to assume that A times B is invertible. That is also something that I know. I'm assuming that A times B is invertible is true, and then using that to show that B is invertible. Okay, so what I want to show, I just said it, is that B is invertible. That is the conclusion I'm hoping to show. So B is invertible. That is called the conclusion. That's what I want to show in this if-then statement. Okay. So after we write down the preliminary stuff that we know and the preliminary stuff that I want to show, then what I do is I'll usually start working with the stuff that I know and see if I can explain what this means. So for example, out of these two things, A and B are n by n, and A times B is invertible. The thing that gives me more information is the fact that A times B is invertible. So what does this tell me? Well, it tells me a lot of things. In the invertible matrix theorem, we saw that when a matrix is invertible, that's equivalent to a lot of things. But there's a reason I sort of mentioned this specific part of the invertible matrix theorem for this example. It's because this part of the invertible matrix theorem is going to be useful to us. So I'm going to keep that in mind. Okay, but for our purposes, when a matrix is invertible, just by the definition of what it means for a matrix to be invertible, we know what this means. This means that there exists an n by n matrix that is the inverse of this. So how do I write that? N by n matrix. Let me just call it W, such that, and what does it mean for W to be the inverse of AB? It means that when I multiply W on the left of AB, that equals what I get when I have AB and I multiply W on the right, and both of those are supposed to be equal to the identity. Okay, so I have taken one of the parts of what I know, and I've explained what that means. At least I've explained one thing that this means. When AB is invertible, that means this statement in gray. Okay, so at this point, what I might ask myself is like, well, what does this thing mean? What does this thing in gray mean? And if I'm able to determine that, I might be able to get something else that I know. Well, let's say I got stuck at this point. Let's say I got stuck here. If I get stuck working with the no side, what I can do is I can work with the want to show side and ask myself, okay, is there something that I could show that would tell me that B is invertible right away? And for this, let's use this part of the invertible matrix theorem. So we could show that B is invertible. This is true if and only if, and it's an if and only if because the invertible matrix theorem has an if and only if statements. So B is invertible if and only if. One of the equivalences is if we can find a matrix, let me just call it D, such that, so either when I multiply D on the right-hand side of B, if that equals the identity, so that would be this statement here. So if I multiply a matrix on the right-hand side of A, if that equals the identity, then A is invertible. That's what this part of the invertible matrix theorem says. So if I can do that, or if I can show that, oh, there's a matrix D that I can multiply on the left-hand side of B. If that equals the identity, in either scenario, either this one or this one, B is going to be invertible. So that's what this part of the invertible matrix theorem says. Okay. So if I can show this thing right here, I'd be done because that implies that B is invertible. In fact, it's equivalent to showing that B is invertible. So now let's see if we can connect, something in the no column with the want to show column. And specifically what I'm going to be able to connect is, I'm going to be able to connect this statement right here with this statement over here. So let's see if we can connect these. Okay, so one thing that I notice is, ultimately what I'm trying to do is, I'm trying to show that a B times something, either something on the right or something on the left, equals the identity. And do I have that in these statements about W? Well, in this statement over here, B is being multiplied on the left and on the right to get the identity. So I'm not super sure that that one is useful. I want to show that B is either multiplied only on the left to get the identity or only on the right. But I do see that in this statement, because B is being multiplied only on the left to get the identity. And that is the key. That is what is going to form the connection with this gray statement. So basically, the matrix D that I want is this thing that I've boxed here, W times A. And now that I've seen the connection, I am ready to write up these steps in a proof. Okay, so the scratch work is not my proof. It was just me jotting down the key ideas that I'll need to generate the proof. So anytime I write up a proof, it's important that I write down my reasoning in complete detail. So I should do things like write complete sentences. That's important. It's kind of like formulating an argument when we do a proof. Complete sentences, use proper punctuation whenever possible. So I'm going to try to do that as much as I can here. But I have the key steps done in the scratch work. It's just a matter of writing them out now in the proof. Okay, so I'm going to begin by saying, well, since A times B is invertible, because that's sort of where my argument begins. Since A times B is invertible, that means, just like I did in the scratch work, well, what did that tell me? That told me this thing right here. So I'm going to write that just in a complete sentence. There exists an n by n matrix W such that A times B times W on the right equals W multiplied on the left-hand side of A times B. So both of those equal the identity. So again, this isn't stuff that's new because I did it in the scratch work, but in the proof, I have to write this up in a nice formulaic way that is easy for the reader to understand, well, exactly how am I connecting what it is that I want to know with what I want to show. because it's a lot harder to follow that argument just by looking at the scratch work. And that's where the proof comes into play. Okay. So now, just like we did in the scratch work, we need to say something like, oh, well, this is sort of that matrix that shows that I multiply B by, that shows that B is invertible. So I would sort of notice, actually no, it's better to, I think a better connecting word is since. So since W times A times B, so I'm using this part right here, I've just moved the parentheses around. Since W times A times B equals that identity, and the other part that I need is this matrix that I'm multiplying by needs to be square. But all the matrices here are n by n. So this matrix is also going to be n by n. And, whoops, I should say WA is n by n, and WA is n by n by the invertible matrix theorem. Let's zoom out so I can refer to that. So which part of the invertible matrix theorem are we using? So we're multiplying B on the left. So we are using this part of the invertible matrix theorem. I'm multiplying my matrix on the left. Okay. So I can say that B is invertible at this point. It's invertible, and that is what I wanted to show. It's invertible, so I'll write something like as desired. That's what I wanted to show. Let's zoom back in. This is a little bit hard for me to write, so zoomed out. Okay, so because B, I can multiply it on the left by a matrix, by a square matrix, to give me the identity, that means that B is invertible. That was one of the parts of the invertible matrix theorem. So at this point, I'm actually done with the proof. I have shown what it is that I wanted to. So it's really common in math that when we finish a proof to write some sort of symbol to indicate that we're done with the proof. So one really common symbol is we write a square and we shade it in. And this is just a symbol for done with proof. So sometimes with proof problems, there's more than one way to do a proof. And with this problem, there is as well. So I'm going to call this, what I did up here, I'm going to call this method 1. And I'm going to show you guys one other way that I could have done this proof. So this is going to be method 2. So method 2. In method 2, we're going to do something called a proof by contradiction. Okay. So proof by contradiction is a really common proof technique. So I'll first explain how that works. Okay, so I've sort of copied the problem down one more time, and let's talk about what a proof by contradiction is. So with the proof by contradiction, what you do is, there's sort of two steps. You assume that what you want to show is false. Basically, you assume the opposite of what you want to show. And then what you try to do is show this leads to a contradiction. Show this leads to a contradiction. And if that's the case, if that leads to a contradiction, it means that the assumption that you began with, you assume that what you wanted to show is false. That is wrong. And if that's wrong, that means what you wanted to show is actually true. And that will complete the proof. Okay, so what does that look like? Let's do a proof by contradiction for this problem. Okay, so proof. So if I'm doing a proof by contradiction, I normally like to begin with a sentence like, assume for the sake of contradiction that, so what is the opposite of what I want to show? I want to show that B is invertible. Well, let's assume that B is not invertible. That B is not invertible. And if I wanted to at this point, I could write up some scratch work, and I could, keep in mind that this is now what I get to assume to be true. I'm assuming that B is not invertible, and then see what that tells me. And that might be a good exercise to do, to pause the video at this point for about a minute or two and think about, well, what does this mean? What if B is not invertible? What is something that tells me? And how could I maybe get a contradiction using that with something that I'm sort of given to be true in this problem? Like, for example, I'm given that A times B is invertible. Could I maybe contradict that? So think about what B is not invertible means. Pause the video for about a minute and think about what that would tell me, and how that could be used to, for example, show that A times B is not invertible. And that would be bad. That would be a contradiction. Okay, so 4, 3, 2, 1, pause the video. Pause the video and think about it for about a minute or two. That's really important in these proof questions. They often take more time to think about, so I'm really going to encourage you guys to pause the video and think about them during these videos as well. Okay, so it turns out once we have the idea, it's actually very short. If B is not invertible, one of the things that this means, one of the things that this implies is, this implies that the equation B times X equals 0 has a non-trivial solution. So this is true for some vector X that is not equal to just 0. Okay, so one of the ways that I could contradict the fact that A times B is invertible is I could show that when I form the equation like A times B times some vector equal to 0, that this is going to have a non-trivial solution. And I could get that really quick from this equation by multiplying both sides by A on the left. So then if I multiply both sides by A on the left, and anytime I multiply an equation on both sides by a matrix, I have to stay consistent with which side I multiply on. So if I multiply on the left on one side, I have to multiply it on the left of the other side. So I multiply both sides by A. So this implies that A times B times X equals, and what's A times 0? Well, that's just 0. So what I've just gotten is that A times B times X equals 0. And recall that X is not equal to 0, which means that this homogeneous system has a non-trivial solution. And because there's a non-trivial solution, that means my matrix, in this case it's A times B, is not invertible. So this implies that A times B is not invertible. Let me give myself a little bit more room to write here. But we've shown that A times B is not invertible, but that contradicts what I was given. I was given that A times B was supposed to be invertible, which is I'm going to put this in red, which is a contradiction. So when I get a contradiction, that means the assumption that I began with. So here's the assumption that I began with. I assumed that B was not invertible. That assumption is wrong. And if that's wrong, that means B is invertible. So let me say, it follows that our assumption was wrong, which means it follows that B is invertible. B is invertible. And that is what we wanted to show. So at this point, we are done with proof. So I write my little symbol to indicate that I'm done. But the key takeaways that I want you guys to have from this is, one, there's more than one way to do a proof question. And I showed you guys 2 ways that we could tackle this problem. The other key takeaway is, when you do a proof problem, doing scratch work to organize our work and think about what it is that we know and what it is that we want to show is often very helpful.